Welcome to the U.S. Geological Survey in another installment of our monthly public lecture series. It's always a pleasure for me to introduce the speakers and to see all of you each month. My name is Leslie Gordon, and as usual, I always have announcements because I want you to come back and listen to us next month and the following month. There's something that's not part of our lecture series, but that's happening in this room next week on Wednesday, April 29th at 6:30 in the evening. The USGS is partnering with the local Menlo Park Fire Department, and there's an event here for local emergency response for neighbor groups, CERT, the community emergency response teams, to be prepared for events such as earthquakes. So if you are at all interested in learning how you and your family can be more prepared, be here in this room next week on Wednesday the 29th at 6:30 in the evening. Next month's lecture, I want to call your attention. It's not on the last Thursday. I think it's the third Thursday. It's May 21st. It will be about the San Andreas Fault, a lecture called Breaking Badly, Forecasting California's Earthquakes. Morgan Page, a geophysicist with the USGS in our Pasadena office, will be traveling up here, so please do join us next month to learn about California's earthquakes.
What was that date again?
May 21st. And in case anyone didn't notice, there are flyers on the table in that corner of the room. Not only flyers for next month's talk, but there are some handouts and fact sheets relevant to tonight's presentation about Lassen Peak, its last eruption, and about the USGS California Volcano Observatory and how we monitor quakes. Okay, so run back, get those before they all go away. Sorry, I'm just poking fun.
There's a ringer in the audience.
Actually. Okay, so enough about earthquakes. Did you also know that California is volcano country? And in fact, volcanoes erupt in California just about as frequently as there are major large earthquakes in the state. And a lot of people forget that we have active volcanoes. Well, just 100 years ago, Lassen Peak erupted, and that's what we're going to be talking about tonight. I do want to point out that there are many, many events that are scheduled within the next month, within May, to commemorate this centennial, not only here in Menlo Park, but especially in the Lassen Volcanic National Park. So if you're not doing anything on the Memorial Day weekend, it will be a lovely weekend to visit the park. Come with us, go on some hikes to Sulphur Works and the devastated area, and do join us this week and learn more about Lassen Peak. So tonight's speaker is Michael Klin. Michael is a geologist here with the U.S. Geological Survey. He's been with us for 45 years. He has degrees from UC Santa Cruz and San Jose State University. He received his PhD at UC Santa Cruz in 1993. Maybe, I don't know, that wasn't that long ago.
45 years.
Not 45, actually. Now that I think about it, it's less than 25. Mike is what I call a traditional field geologist. He still goes out in the field and looks at the rocks. He's not someone who just sits in front of a computer and does numerical modeling, which a lot of folks do. His specialty is young volcanic rocks, especially in the Cascade Range, including Lassen Volcanic Center and Mount St. Helens. So without further ado, I'd like to introduce Mike Klin, who's going to speak about a site fearfully grand, the eruptions of Lassen Peak from 1914 to 1917. Please welcome Mike Klin.
Well, thank you, Leslie, for those kind words. Next month, the National Park Service will be celebrating the 100th anniversary of the May 22nd eruption of Lassen Peak, which was the last in the continental United States before Mount St. Helens erupted in 1980. A variety of accounts and interpretations of the eruptions were published in the years shortly after 1915. Most have flaws for a variety of reasons. One was the lack of volcanology experience of the scientists of the day. Another was failure to recognize critical evidence in the deposits. And there was considerable misinterpretation of the photographs that were available at the time. This work on the 1915 eruptions was done in the mid-1980s with Robert Christensen, who's another geologist here in Menlo Park. And he deserves considerable credit, maybe more than half, for the interpretations that I'm going to talk about today. We had the advantages of modern volcanology, understanding how volcanoes work, analytical techniques, which are much easier to do now than they were 100 years ago, and we had the photographic record, a more complete photographic record than the early geologists, and still reasonably well-preserved deposits. The total volume of this eruption was on the order of 0.02 cubic kilometers. A tiny eruption compared to something like Mount St. Helens, which was about a cubic kilometer. So 25 or 30 times smaller than the 1980 eruption of Mount St. Helens. Today, the deposits are rapidly becoming obscured by vegetation and erosion. And this event was one that will not be well preserved in the geologic record. So if you come back 1 million years from now, it's not one of the ones that you're going to be able to see and record as part of the history of the Lassen Volcanic Center. Well, Lassen Peak is part of the southernmost, it is the southernmost active volcano in the Cascades. It's part of the Lassen Volcanic Center, which is an area of volcanism rather than a single volcano. It's located about 70 kilometers east of Redding at about 100 kilometers south of Mount Shasta. Lassen Peak is not a typical stratovolcano like Mount Shasta. It's a volcanic dome, albeit a big one, about 2 cubic kilometers in volume, and it's one of the largest in the world. It's 27,000 years old and had not had an eruption since its 27,000-year-old formation and 1914. So the 1914 to 17 eruptions of Lassen Peak were one of the first to occur after photography became readily available to amateurs. Thus, it was well documented and popularized by the Northern California media, particularly the San Francisco Chronicle and the Sacramento Bee, and subsequently by the popular media. Reporters were in competition to get scoops, to outdo each other. Thus, much of what was reported was sensationalized and doesn't bear the scrutiny of the way news does today. Benjamin Franklin Loomis was a local businessman. He was a Lassen Park supporter and an amateur photographer. He used an 8x10 view camera. So he hauled this 8x10 camera out to the field, which required a lot of big lenses and a big tripod. And he took his pictures on glass plate negatives. So they would haul a tent out there to have a portable darkroom. They'd take the glass plates out, put the emulsion right on the plates in the field, expose them and take the pictures, and then take them back home to be developed. So it was a pretty arduous process in those days, but he was successful in doing this, and he has a lot of good pictures. Many photographers recorded Lassen Peak eruptions, and there's a number of different compilations of photos that you can find in archives today. But Loomis left the most complete and the best documented record. Many of his photographs were published in a book called his book that he wrote, The Pictorial History of Lassen Volcano, which has sold so many copies in the 1920s and 30s that you can find it today on Amazon for relatively inexpensive. And it's been reprinted many times by the Park Service, so there's lots of more modern copies around too. Most of Loomis's pictures now reside in the National Park Service archives, but some have been lost and many were given away. Several of Loomis's photographs were absolutely critical in our understanding of the chronology and processes of the 1915 eruptions. So, what happened? The initial event of the Eruption series occurred on Memorial Day, May the 30th, 1914. Without any discernible warning, there was an explosion at the summit of Lassen Peak. The explosion was viewed from considerable distance. Chester, 30 miles away, and in the northern Hat Creek Valley, also about 30 miles away, and caused considerable consternation among the residents. Many people probably didn't realize that Lassen Peak was an active volcano. No magma was ejected in this explosion or any of the explosions that occurred over the next 11 and a half months. They were driven by blasts of steam, what we call phreatic eruptions or phreatic activity. Phreatic eruptions occur when groundwater in the volcano is heated under pressure to temperatures higher than boiling. And when it works its way to the surface and encounters lower pressure, it explodes, flashes to steam and explodes. Think of it like taking the lid off a pressure cooker while it's still hot. You're going to make a mess in your kitchen. This Loomis photograph was taken from Manzanita Lake about 6 miles from Lassen Peak. It shows a phreatic eruption that occurred on June 14th, 1914. There were no earlier pictures from the explosion that occurred 2 weeks earlier. This location was a popular spot for people to come and watch, to set up their cameras, wait for something to happen, and take pictures because it was safe, far enough away, and it had a good view of the volcano. One of the things that you can see in this picture here is this ring at the bottom of the explosion. This is a base surge, which is the part of the explosion that comes out at the base of the erupting column. This was a phenomena that was not recognized at the time, and until careful observations of atomic bomb tests, base surges and explosions were not well explained. This slide shows 6 successive views of the same explosion that you saw in the previous slide, which was this picture. It starts in frame 1 with the vertical directed eruption column of steam and ash. A few minutes later, this one was taken. A few minutes later, this one was taken. And then in the 4th frame, a second eruptive column is coming out. Altogether, these 6 photos show about 20 minutes of activity. And the explosions sometimes occurred in quick succession like this, 2, 3, 4, even 10 in a row. But at other times, over the next 11 and a half months, nothing happened for days or weeks at a time. So they were intermittent. The steam explosions blasted a crater at the summit of Lassen Peak. The crater was first observed the first day after May 30th, when it was very small, only about 20 feet in diameter. There had been no crater previously at the summit of Lassen Peak. It had not had an eruption in its 27,000-year-long history. Loomis and a party of locals climbed the volcano on June the 20th, took these pictures. Fortunately, it didn't erupt while they were there. And of course, in today's atmosphere, or today's bureaucracy, nobody would be allowed to do that. Yeah. We'd be flying around in helicopters watching it. Yeah. Note here, this is the summit of Lassen Peak. Note the cragginess of that original outcrop. And here you can see deposits of rock and ash thrown out of the volcano. And note how thin they are. This is a very early picture in the history of the crater. Well, the phreatic eruption clouds consist mostly of steam, but they also contain ash, small sand-sized particles of rock, derived from pulverized rock that's ground up in the crater by the steam venting, and blocks of rock that are thrown out in the eruptions but only travel a short distance. These blocks peppered the lookout at the summit of Lassen Peak and eventually completely destroyed it. Here we see 4 successive views of the lookout prior to May 30th, in October, about 5 months after the eruption started, and then in August of the next year. By that time, it's completely gone.
I didn't know they had, on August 1915, I didn't know they had laptops there.
Apparently that's not a computer. But I can't tell you what it is. Here's another view of the crater on October 12, 1914. You can see now it's much bigger. You can see in the wall of the crater here is the old rock of Lassen Peak, that light-colored dacite that forms Lassen Peak. And you can see that the deposits at the top of the crater wall are getting thicker. This picture was taken a little bit later. And now, see, looking at the summit of Lassen Peak here, how smoothed off it is from deposition of ash on top of the craggy outcrop. And you can now see the crater wall deposits are even thicker than they were before. So, in mid-May of 1915, after 11.5 months of phreatic activity, the character of the eruption changed dramatically. Beginning on May 14th of 1915, incandescent glow was seen at the summit of Lassen Peak, mostly reflecting off clouds. And it was seen from Manton, a small town about 20 miles to the west of Lassen Peak. Well, this meant that magma had appeared in the crater, and it was filling the crater and building a small lava dome. Over the next 6 days, the small lava dome got bigger and bigger until on the evening of May 19th, it was overtopping the edge of the crater, and blocks of rock, hot rock, that were red were seen bounding down the slopes of Lassen Peak. This is a picture of what the now devastated area looked like before the 1915 eruption. It was an area of mature forest, primarily red fir and mountain hemlock. Those trees were hundreds of years old. Late in the evening of May 19th, there was a large explosion at the summit of Lassen Peak. The winter of 1914 and 1915 was an El Nino year, and there was about 30 feet of snow on the upper flanks of Lassen Peak, which is a lot of snow. So hot blocks of rock from the dome that was fragmented by this eruption fell onto the upper slopes of Lassen Peak and started an avalanche of snow carrying the hot blocks of dacite that roared down through the mature forest on the northeast flank. Trees were ripped out of the ground and carried along in the avalanche. Melting of the snow by hot blocks created a mud flow that quickly followed the avalanche. This Loomis photograph, taken on the morning of May 22nd, 3 days later, shows the path of the May 19th avalanche and mud flow on the northeast flank down to the lower slopes of Lassen Peak. This area is now called the devastated area. Here's a schematic geologic map. Summit of Lassen Peak is here. This darker pattern marks the path of the May 19th avalanche. It came down, devastated area, parking lot is right here. This area is a small recessional moraine about 50 feet high. A moraine is a pile of rocks left by a glacier. There were glaciers here about 20,000 years ago. And it just went right up over that little moraine and down into Hat Creek and ended up about here. It came to rest and immediately started to melt a lot of the snow because of the hot rocks in it, and that created a flood that went down Lost Creek, or Hat Creek. Immediately behind the avalanche was a large mud flow that was created by melting of the snow that was in the avalanche deposit. The mud flow didn't have enough strength to surmount Emigrant Pass, so it was diverted and turned and went down Lost Creek. Here's a view down Lost Creek of the area that the mud flow went through. And if you look at this tree over here, you can see that the bark on this tree has been smashed off by rocks in the mud flow and trees that were being carried by the mud flow and bashed into this tree, but didn't take it out. What this indicates is that the thickness of the mud flow as it was traveling down Lost Creek was 18 to 20 feet deep, even though it left a deposit that was only a few meters thick, or maybe 5 or 6 feet thick, depending on where you dig holes in it. So this just shows that mud flows pass as a big wave as they go down drainages. You probably can't see this picture very well because it didn't come out very well, but this is another geologic map, and I just want to show you how far the mud flow went on this. Here's Lassen Peak. Here's the devastated area parking lot where we just were. We're looking down Lost Creek in that last picture. The mud flow went down Lost Creek for about 15 kilometers out to about here, where it stopped. And mud flows are just full of water. They have about 50% water, sometimes more than 50% water. When they come to a stop, all that water is released. And there was a big flood that went further down Lost Creek and Hat Creek on the evening and early morning hours of May 19th and 20th. This caused some damage to homesteads down in Old Station and in the Hat Creek Valley. And the very muddy water killed fish in Hat Creek as far north as the Pitt River, where Hat Creek joins the Pitt River. There were fish kills. And we know this because the California Fish and Game Commission was alerted, and they went and checked all this out. And they were worried about poisonous gases and poison in the water. It turns out it was just the mud and lack of oxygen in the water that killed the fish. Well, these mud flows are capable of carrying huge blocks of rock. Many of the huge blocks of rock that you see in the mud flows are derived from talus slopes of Lassen Peak. They were old 27,000-year-old Lassen Peak material, but many of them are pieces of the dacite dome that had been growing at the summit and were disrupted and thrown onto the upper flanks of the volcano. This rock, which is about 20 feet in diameter, weighed about 100 tons. So it takes a big chunk of stuff, flowing mud, to carry something that big. This is called hot rock. It's now a tourist attraction in the park. It was called hot rock because it was still hot for several weeks after emplacement of the mud flow. And this is just internal heat from emplacement as a lava dome that it takes. Rocks are insulators. It takes a long time for that heat to get out. Here's another view of the margin of the mud flow in the Lost Creek Valley. All the trees that were ripped out from the mature forest on the flanks of Lassen Peak and in Lost Creek Valley floated in the mud flow, and as they go down, they're sort of pushed to the sides, and they pile up on the margins of the flow. And you can actually use them to map where the flow went and where it didn't. There were many piles of trees like this along the margins of the mud flow into the 1980s, 1990s, and that's about how long it takes for trees to decay at Lassen. And now they're disappearing, and they're becoming piles of wood rather than nicely formed logs. You can also see Lassen Peak in this picture, still steaming in the background. Another feature of the mud flows are these little craterlets. These were formed by blocks of rock, the hot rock, that were left behind, buried in the mud flow, that boiled water in the mud flow, and when that steam vents at the surface, it creates these little craters. These were, I don't know whether anybody said anything about them in 1915, because I just found this picture relatively recently. But at Mount St. Helens, these were quite common in 1980, where they were created by blocks of ice that were in the deposits, which boiled and vented and created these little craters. Here, there wasn't any ice on Lassen Peak to have formed these, so I think they were formed by hot rock that boiled water. Well, the explosion that disrupted the lava dome and the summit at the summit and precipitated the avalanche and the mud flow also reopened the conduit that had been underneath the lava dome that formed at the summit. And more new lava came out and filled up the summit area and created two lava flows as it spilled over the margins of the crater rim. One on the west side, which you can't see in this direction, but one on the northeast flank, which you can see here in this picture that was taken on the morning of May the 22nd. The original glass plate of this negative, or the original glass plate of this picture, was one that was lost a long time ago. Perhaps Loomis gave it away because he didn't like this fogged corner up in here, but he was wont to give away many of his pictures to his friends, family, etc. There is another picture taken from the same spot at the same time in his book that doesn't have this fogged corner, but it's taken at a slightly different time, and this steam cloud that you see at the summit here is in the way of seeing the lava flow. It turns out that being able to see this lava flow that was still in place on May 19th is important in our understanding of the history, and I'll get to that later. Well, prior to our rediscovery of this picture, most volcanologists attributed the May 19th mud flow to the lava flow coming out onto snow, not being stable, and collapsing and starting the avalanche. Here we see the avalanche and the lava flow still in place, so obviously it did not cause the avalanche. After May 19th, there was no further activity for 2 days. On the morning of May 22nd, Loomis visited the devastated area and he took this picture. Note also this rock in the foreground here. We're going to see that in some other pictures. And they left the area about noon after running out of glass plates. About 4 o'clock or 4:30 in the afternoon of May 22nd, after Loomis had left, a large vertically directed eruption column of dacite, pumice, ash, and gas rapidly reached a height of about 30,000 feet. The eruption lasted about 30 minutes. This view of the eruption column is taken from the Sacramento Valley about 50 miles west of Lassen Peak. It was taken by a guy named Stinson. Here, the eruption cloud is seen to be still expanding upwards and is bending over by being blown in the wind toward the east. Another photograph taken slightly later shows the eruption column after it's reached its maximum height and is spreading out at the top. Basically, it's lost its upward momentum and is spreading out just like you see atomic bomb columns do. This picture looks fake, doesn't it? Well, it is. Loomis was very unhappy that he didn't get any pictures of the eruption. This was taken by a guy named Myers from the Sacramento Valley near the town of Anderson. Loomis bought it from him because he wanted to have a monopoly of the pictures so that he could sell them. And he actually created a lot of postcards and sold pictures in the Park Service for quite a while. But he didn't like the foreground on the Myers picture, so he photoshopped it. Basically made a copy negative, put a new foreground on the eruption column, and stuck the mushroom cloud picture onto his own background. So it's a real picture, but it's been messed around with. The important part of it is that it shows the eruption column at its maximum height, which is estimated to be about 30,000 feet. Here's a view from downtown Red Bluff, which is about 60 miles southwest of Lassen Peak. The eruption column was visible from much of Northern California, as far west as Eureka on the coast, and at least as far south as Sacramento. I haven't been able to accumulate any evidence that it was any further south at Sacramento. Well, partial collapse of this big eruption column produced a pyroclastic flow. And that pyroclastic flow is a flowing mass of hot pumice and gas that's driven by gravity. So it flows down the flank of the volcano, and it gets down to the flat, it spreads out. It basically followed the same path as the avalanche 3 days earlier. In the area affected by the pyroclastic flow, the trees were blown down by the shock wave that advances in front of it. shockwave shears off the trees, leaves behind stumps that are still a few feet high, and leaves the trees laying on the ground, pointing away from the direction that the pyroclastic flow was coming. You've probably all seen the pictures of Mount St. Helens with the forest that was knocked down, where the trees are all in big waves following the topography. Here, it was much flatter than it was at Mount St. Helens, and the trees are all basically pointing away from Lassen Peak. In contrast, and this is in contrast to the mud flow path, which rips the trees out and carries them away. The pyroclastic flow covered a much wider area than the avalanche on May 19th, and it passed over areas that were still covered with lots of snow. The hot gas in the pyroclastic flow melted this snow and generated another mud flow. This mud flow followed the same path as the one on the 19th, went down Lost Creek, went about 5 kilometers further than the May 19th one because it had more water in it and it was more mobile. And when it came to rest, it released water that created another flood in the Hat Creek Valley. Most of the people that lived in the Hat Creek Valley at that time had experienced the first flood, and they were out of town. And so there was not, and there were no injuries in any of these eruptions other than a few minor things about people running away from the mud flow and tripping and getting their feet cut because it happened at night and stuff like that. There were no serious injuries and no deaths. The mud flow, it followed the same path, and yeah, I already said that. The pyroclastic flow and the mud flow affected the same area where Loomis had taken his picture. This is a second picture taken on June 1915, after the May 22nd eruption. If they had still been there, he would be dead. If they had still been there when this eruption occurred, they'd be dead. Fortunately, Loomis and his party were back at Manzanita Lake at this time. Unfortunately, they had no glass plates left to take new photographs. This photo shows the much wider area affected by the pyroclastic flow and the fluid mud flow than the avalanche and mud flow of the May 19th. And we'll compare the pictures in a few minutes. Note that the lava flow is still that was still in place on the previous picture is now gone in this picture. The May 22nd eruption basically blasted the lava flow off the summit of Lassen Peak, and it was incorporated into May 22nd deposits. This picture is the one that most geologists in the early days looked at, saw that the lava flow was gone, didn't necessarily recognize that there were two eruptions, and therefore interpreted the origin of the mud flows as destabilization of the lava flow. Well, that big eruption column was still full of pumice and ash and gas, and a lot of it fell on the upper slopes of Lassen Peak. The big stuff, the meter-sized blocks and the football-sized blocks of pumice, don't travel very far, and they fall back on the volcano. They fell onto still much snow-covered areas and created a number of smaller mud flows later on in the evening of May 22nd. Here you can see 3 of those mud flows, one over here, one coming down here, and one coming down here into Manzanita Creek. These were very viscous. They didn't have as much water in them. They're not very mobile. They have a lot more rock in them, and they don't flow very far once they get to the flat. They basically went to the base of the volcano and stopped. That big eruption column was also blown to the east. This figure shows areas that were documented to have ash fallout, mostly on the next day from May 22nd. This map was compiled by Jonathan Davis in the 1980s from contemporary newspaper reports. So Lassen Peak is here. On the actual edifice of the volcano, the pumice is about 30 centimeters thick. As you get about 25 miles away, it thins to a deposit where you can't really find a continuous layer of pumice anymore. That's about how far we can track it today. But ash fell over this large area, including probably a millimeter or so in Winnemucca and traces of ash even further than that. Most of the volume of that big eruption cloud is in the distal component of the ash. Very little of it, volume-wise, falls on the volcano itself. Okay, so now I want to compare the two eruptions from May 19th and May 22nd. Here's the May 19th picture. And here is the pre-1915 view of Lassen Peak superimposed on that picture showing where the forest was. You can also see behind it that there's no vegetation left. In particular, pay attention to these three areas of forest that are still in place on the morning of May 22nd, over here on the east side of the devastated area and on the lower flanks of Crescent Crater. When we put the two pictures from May 19th and post-May 22nd together, you can see that here's these areas of trees still in place. Now you can see that those trees are gone here and over here. So it's pretty clear that the area that was affected on May 22nd by the pyroclastic flow was a much broader area than was affected on May 19th. Well, after May 22nd, the magmatic part of the eruption was over. It had built for a year up to the magmatic part. The magmatic part lasted about 10 days, and then the activity returned to phreatic and declined over the next few years. There were a number of phreatic explosions beginning right away after May 22nd and continuing into about October of 1915. And there was renewed activity in the spring of both 1916 and 1917, especially in 1917, when a new crater was blasted out at the summit of Lassen Peak by these phreatic eruptions. Then the volcano went into repose, but there was still a lot of steam emitted into about 1921. If you read a lot of the history of Lassen Peak, they'll tell you that the eruption continued until 1921. But in fact, these were mostly just big volumes of steam that were being emitted in the late 19s and into 1921. There was no explosive activity after June of 1917. Well, what I'd like to do now is show you a few pictures of recovery of the devastated area. Recovery has been very slow, and that's because the area was completely buried by these sterile lahar and avalanche deposits. The old soil is several feet or meters below the ground, and it's really difficult for new trees to get started growing in this barren substrate. It takes a while. Once they do get started, they start to create soil, and which holds moisture and provides fertility. And annual plants, especially lupin, for example, provide nitrogen that are necessary for the trees to get going. Once they do get going, they start to provide protection for each other from the elements. The wind and snow that this area gets a good 8 or 10 feet of snow every year, buries those little trees and can kill them. One interesting thing to note about recovery of the area is that most of the trees that started growing in the lower devastated area were trees that you normally find at much higher elevations, like red fir and mountain hemlock. Apparently what happened is that seeds were carried by the pyroclastic flow from high up in the slopes of the mountain and deposited in the lower slopes. Today, new trees that are growing are the white fir and Jeffrey pine that are typical of this elevation, and they grow much faster than those trees from higher elevations, and they're shading them out and killing them. So this is a true forest succession kind of situation that's going on here. This view, this view was taken in 1948 by a park naturalist named Lynn, who was also an accomplished photographer and took a lot of pictures of the Lassen Peak area. And note that this picture was taken from the same spot as the Loomis photographs. Here's the same rock that's in the Loomis photograph pictures. And this rock today, when Bob Christensen and I rediscovered this rock in the early 1980s, the Park Service said, "Oh, that's cool. We didn't know where that was." And they needed, at that time, it was a time when they were trying to develop handicapped accessible trails in the park. So they said, wow, this is relatively flat surface. This would be a great place to put a handicapped trail in. So what they did, and it's only a few hundred meters from where the parking lot is, what they did was built this handicapped trail that was wheelchair accessible for people to go and make a little tour around the devastated area and see the various deposits and rocks and go back to where the Loomis pictures were taken and things like that. One of the issues with the Park Service is that they have very rapid turnover of personnel in parks. And a lot of information that's developed by park naturalists or accumulated by park naturalists is lost when these people go to other parks and new people come in. It gets stored away in file cabinets and stuff, but a lot of people don't access it. So it's been really interesting for me to work with the Park Service on these kinds of projects because I have the accumulated 30-year-long knowledge of information that they could have access to, but they just don't bother. This picture was taken by Bob Decker, who was another famous survey geologist in the 1950s. And it shows how many trees are actually starting to grow about 40 years after the eruption. But they're small. They're basically waist-high trees. Today, if you go, this picture was taken in the 1980s, and it shows the devastated area parking lot and the view of Lassen Peak. If you go there today, those trees that are in the foreground have grown up so much that Lassen Peak's barely visible from the parking lot. And if you go back to the Loomis Hot Rock, Lassen Peak's not visible at all. I think it would be really interesting for the Park Service to take out a few of those trees so that they could have a nice exhibit. Well, I've given you a pretty good overview of the eruption, but I want to talk a little bit about what it is that allowed us to put together the story of the eruption and improve upon the work that was done by early geologists. So here's one line of evidence that is interesting. In most years, the summit of Lassen Peak is partially snow-covered, even at the end of summer. However, during the drought year of 1986, the summit area was nearly devoid of snow, and a critical relationship in the deposits was exposed. In this photograph, you can see the explosion deposit, which is this berm of material here. This is the explosion that destroyed the May 19th lava dome. And you can see that it's overlain by the lava flow here. So this particular deposit had not been recognized by previous geologists, and that's why they didn't have any mechanism to explain the May 19th avalanche and mud flow, because it just hadn't been visible to them in the past. And here we have it underneath the lava flow that came out on the same evening, but they had attributed the avalanche to the lava flow coming out on snow, but we've already shown you in the picture that that can't be right because the lava flow still existed on the morning of May 22nd. Well, this kind of information and a few other things, for example, the presence at the summit of the remnants of a lava dome. This was recognized by previous geologists, but they didn't really pay any attention to it, and they didn't recognize that it had been partially destroyed by an explosion. The explosion deposit at the summit of Lassen Peak, which I just mentioned. Another thing that we found were large blocks of dacite that were deposited on the ground surface in areas that were beyond where the mud flows went. So the mud flows down here in the trees. This is old surface. It's actually avalanche surface. And here's this big block. It's about 10 feet across of dacite. It's way too big to have been thrown there by any kind of explosion. Well, how did it get there? The deposit that it's in is only a few centimeters thick. Yet, in order to carry a block of rock this size, whatever the flowing deposit is has to have enough matrix to be thicker than the biggest blocks that it's carrying. Otherwise, they sink to the bottom and they drag on the ground and drop out of the deposit. And in fact, that's how they drop out of the deposit here, because this is a place, this is Immigrant Summit, and it was going up over the summit. When that block grounded, it stopped. Well, how did they get there if they weren't carried by a mud flow? They must have been carried by some deposit that was inflated enough to be that thick, but left no deposit behind. The obvious answer to that, although it wasn't obvious at the time, is snow. This was being carried in a snow avalanche or a snow matrix avalanche. And after we spent a lot of time looking at these deposits, we figured out that that was in fact the case. This, to my knowledge at that time, had not been explained in the geologic literature, but we subsequently found that other people have found these kinds of deposits, particularly in South America on big volcanoes that have lots of ice and snow on them. A couple of other things that we recognized were that the May 19th and the May 22nd deposits have dacite in them with different characteristics. This was not previously recognized by previous geologists. So I can now go out there and pick up a piece of rock and say, oh, this is May 19th, or oh, this is May 22nd. That, in combination with the Loomis photographs, allowed us to determine which deposits were emplaced on May 19th and which ones on May 22nd. So it's a bit of geologic sleuthing that we sometimes can do and sometimes can't. But the key issue here is that the Loomis photographs were absolutely critical. In particular, the one that shows the lava flow still in place on May 19th, before any May 22nd deposits were erupted. So we know that the deposit that's there at where that rock is was emplaced on May 19th. So that's the end of my story. But before I finish, I'll say, will Lassen Peak ever erupt again? And the answer is probably not. But the Lassen Volcanic Center is active, and it will erupt again. It's only a matter of time. The Lassen Volcanic Center has had at least 13 eruptions in the last 100,000 years. That doesn't sound like very often. It's a recurrence interval of about 7,500 years. However, there's been 3 eruptions in the last 1,100 years. Chaos Crags is 1,100 years old. Cinder Cone erupted in 1666 AD, and the 1915 eruption. So the eruptions are not evenly spaced in time. They clearly occur in groups, i.e. the volcanic activity is episodic. Also in the area surrounding the Lassen Volcanic Center, there have been at least 58 eruptions that we have recognized in the last 100,000 years. These are smaller, basaltic, Hawaiian-style volcanism. And that's a recurrence interval of about 1,500 years. These also occur in little bunches. They're episodic rather than spaced out evenly in time. So Lassen will erupt again, and maybe if some of us are lucky, it'll be in our lifetimes. Thank you.
I think Mike would be happy to entertain questions, and as usual, so that everyone can hear you, including those of you who are watching online, please use the microphones. There's one in that aisle and one right over here in this aisle, and we'll just go back and forth. Why don't you start the first question over there?
I saw the devastating area first in about 1962, and was amazed at the difference when I went back in the late 80s at how much it had grown up. I thank you very much for telling me what caused it to wait so long to start. But do you have a fairly current picture of it at all? The latest one I saw up here was the 1980-something, and I've seen it that way. But you're saying it's totally invisible? Are they doing anything to preserve it at all?
No, the park is using it as a natural resource area, research area, to allow it to recover naturally. That's the way the park operates.
Well, it was an amazing difference, so I thank you for telling me about why it took so long.
Yeah. Why did Loomis use wet plate glass, which was an obsolete technology by that time? Cut film and roll film were available, and he could have done quite a bit more if he hadn't tried to emulate Matthew Brady.
He probably could have, and I do not know why he used that technique. It's perhaps that he enjoyed working that way, like some photographers do. He enjoyed working with a view camera, and I suppose if sheet film was available, it certainly was available at 8 by 10, and they had film holders, what they needed at that time. So it's a good question. I don't have an answer for that.
Hi, Mike. That was a great talk.
Thank you.
You talked about how that large rock was displaced by snow. And that begs the question, what about the hot rock? I mean, the hot rock could not be displaced by snow because it would melt the snow. Do you have any idea how the hot rock?
Well, there's two factors involved in that. One is the first hot rock was carried by the mud flow, not by the snow matrix. The second is that the snow matrix avalanche must have happened very quickly. It basically was just the head of the avalanche that was coming off Lassen Peak, and the only place that we see it nicely preserved is on Immigrant Summit or Immigrant Pass, where the mud flow did not go. And in fact, what led to our development of that idea was the fact that the mud flow didn't go there, but there were still these big blocks of rock that were carried. And I showed you a picture of one of them, but there are many more. So it must have happened so fast as the thing was actively turbulently tumbling and turning that what you just suggested, that the snow around it would be melted very quickly. Yeah, that must have happened, and that's as far as it got, basically, before that happened.
Hi. I think you said that red fir, I believe the higher elevation tree had come down to lower elevations, was carried by the flow. I would imagine all the seeds would have been sterilized in the flow that hot, so I'm just puzzled about that.
It must be, and it's true, that any seeds that were deposited in the pyroclastic flow would have been sterilized, because we actually find a lot of burnt vegetation in the pyroclastic flow deposits. However, it's very delicately preserved. You can find pine or fir boughs that are still intact with a little twig and all the needles still sitting on it, but completely sterilized. What must have carried the seeds was the shock wave in front of the pyroclastic flow that was not hot.
Hi, thank you for your presentation. I enjoyed it.
Yes, so too.
Oh.
Yes, so too.
Go ahead with your question.
I'll get back to you.
Hi, thank you for your presentation. When you said that this was a lava, a dome volcano, I think you called it.
Right.
Are the Cascades made up of stratovolcanoes and these kind? And if so, why? I don't understand why they have
The Cascades are made up of a whole variety of types of volcanoes. The ones that we see, the famous ones, Mount Rainier, Mount Shasta, Mount Adams, Crater Lake, those are typical stratovolcanoes. They are the ones that everybody sees and are common knowledge of the Cascade Range. And they are spaced out at 50 or 100 miles apart on each one. However, in between those volcanoes are lots and lots of smaller volcanoes that are smaller lava shields, lava domes, cinder cones, and lava flow fields. We only get the big volcanoes at places where there's a lot of magma coming through the crust, and it interacts with the crust and builds this big volcano in one spot. In the rest of the arc, and it's a continuous arc, there are many, many smaller volcanoes. The Lassen Volcanic Center is a little different than most of those big stratovolcanoes because it's a place where there's a lot of silicic volcanism, or volcanism with a much higher silica content in the rocks than the big stratovolcanoes, which are mostly andesites. The silicic rocks are much more viscous magma, and instead of coming out of the top of a lava cone that builds up a big edifice by many, many, many lava flows, these are volcanic domes. The lava is too viscous to flow away from the vent, and it just makes a big pile on top of the conduit. And then the next eruption is somewhere nearby instead of coming out of that same conduit. So there's a lot of diversity in Cascade volcanoes.
Two questions. One a comment and the second a question. On the why was he doing the wet plate process? Notice his birthday. He was around when the wet plate was in wide use. Wet plate is also, you can make your own emulsions. It's a do-it-yourself process. You have more control. You can vary your emulsions. You can make it out of chemicals and so forth. For the do-it-yourself or enthusiast, it would have been more, plus it's cheaper. Cut film would have, would have been pretty expensive in those days. And if you fog it, you're out. But if you with wet plate, just make more. Just all you have to do is the dry chemicals with it.
Good point, and I don't know that Loomis was that enthusiastic about doing it himself, but he may have been.
But he must have started earlier, and I'm guessing here.
Well, no, he definitely started earlier. He was in his 50s at the time of the eruption.
I was noticing his birthday. Is
yeah, I forget when that was.
And then his death in 35 and stuff.
1857 he was born. Okay, so he was in his 50s at the time, early 60s.
The question I have is, what the cause of the Cascade Range? What produced the Cascade Range and the volcanoes associated with it, and if there's any connection with the tectonic plate activity in that region?
Oh, absolutely. The Cascade Range is part of the Ring of Fire, which surrounds the Pacific Ocean, and it's caused by subduction of oceanic plates underneath continental and other oceanic plates. So, for example, the Aleutian chain, the Cascade chain, the chains of volcanoes, the Andes, and all the way around to Indonesia and Japan are all part of the same plate tectonic process. Are caused by subduction of oceanic plates that carry water down into the mantle. That water lowers the melting temperature of mantle rock, and it comes back up to the surface as magma.
Like the pictures on behind that.
Yes, exactly. The picture down there at the bottom.
Thank you.
So you said that the lava cap was still in place after the avalanche. So then where did the heat come to turn the avalanche into the mud flow?
It was contained in the blocks of rock that were thrown out onto the upper surface of the volcano from the growing lava dome.
Okay, but it didn't displace the lava dome itself. There was additional
eruptions. The lava dome is mostly gone. If you calculate its original volume, I think only about 10 or 15% of it is left in place. And in fact, the only way we can recognize it is that the rock in the lava dome has a different character than the rock in a lava flow. It's a different joint pattern. It's much thicker. And you can see, in fact, I probably have
So hot rock was ejected to cause the avalanche?
Right. The explosion disrupted the growing lava dome. Okay, so here is a picture of the summit of Lassen Peak. This is the lava flow in the foreground. This is the May 22nd crater. Here is part of the lava dome. So you can see here a piece, and then you can see some more. This is old Lassen Peak rock here, and you can see some more of the lava dome. So it sat right in this area. It's mostly gone now, and it was still hot. It was only a few days old. It had temperatures of 700 or 800 degrees in its interior. And when that thing was disrupted, all of those pieces of hot rock fell on the upper part of the volcano, into the 30 feet of snow.
So hot lava did erupt, but not at that particular place.
Yeah, well, no, that was hot lava. It just was it was a few days old hot lava. And it was solid because it was below its solidest temperature, but it was still at a temperature of 600 or 700, 800 degrees in the interior.
To melt the snow. Okay, thank you.
Yeah.
With St. Helens, obviously the peak of the mountain was very different after the volcanic action. What was the nature of the peak area before and after? How did that change? What was the elevation of Mount Lassen changed by very much? In other words, what happened to that part of the
well, I showed you a number of pictures early on of the crater area. And the summit of Lassen Peak prior to the eruptions was basically a flat area with a few little peaks on the top of it that were 100 or 150 feet high. The area where the 1915 eruption occurred was a saddle between those two peaks, or three peaks. It was a relatively smooth, flat place. The actual summit of Lassen Peak, the 10,457-foot peak, was not affected by the eruption. It's still the highest spot. The area that was affected was the saddle. It, first of all, was blown out and got lower, but then was filled up by this lava flow. So in this picture, the summit of Lassen, this picture's taken from the summit of Lassen Peak, so it's not in the picture. This was another little high spot over here, and there's another high spot off the picture on this side. But the main difference is that instead of this saddle of old 27,000-year-old rock, you now have this very craggy lava flow at the top and a bunch of explosion deposit on the rest of the summit of Lassen Peak and the craters. This is the May 19th crater was filled in by the lava flow. The May 22nd crater is here, and just over this little divide here, the 1917 crater is on the other side of that. So in the sense of topography, the summit of Lassen Peak was not dramatically changed. In the sense of going up there and seeing a rock that's only 100 years old versus something that was 27,000 years old, I count that as a pretty dramatic change.
Thanks. How long did it take you to do all this work? I mean, was it continuous, or was it just sort of a...
No, it was not
on and
continuous, and that's really a long story. I started working at Lassen in 1975 as a field assistant to a person who was doing a geologic map there. That map was never finished. A few years later, I was asked to start working on that geologic map because at that time I had as much knowledge about the area as anybody else. It took about 10 years to create the geologic map of Lassen Volcanic National Park, 10 field seasons. And I don't have a copy of the map, but I could go get one in my office and we could look at it. And then I spent about another 5 years mostly working in the office, which is the writing and the creation of the map and stuff like that. The actual work on the 1915 eruption took about 3 summers. And it was mostly working with Bob Christensen, who was working on the young deposits at Lassen in those days. So it's continuous in the sense of many years in a row, but it's intermittent in the sense that you can only do this work in the summer. And in the winter, we do things like getting rocks analyzed and stuff like that. It actually turns out that my part of the work on the 1915 eruption was basically its chemistry and petrology. That is the origin of the rocks. What happened to them in the magma chamber and how did they get to the rocks that they are. The Lassen eruption, oops, I went past that. Oop, there it is. The Lassen eruption actually is extremely interesting. It's a classic location of mixed magmas, meaning there were 2 different magma types in the magma chamber that mixed together to form the rocks and produce these 4 different kinds of rocks. This one is the lava dome and the lava flow, which was the May 19th eruption. This lighter colored material is the May 22nd eruption. These are inclusions of basalt that you find in these other rocks. And this is the famous banded pumice, which is part of the 1915 eruption. And it includes both of these 2 different types of magma mixed together, where they were both coming up from the magmatic system in the conduit together. Anyway, that was my part of the eruption. Bob Christensen's part of looking at this was primarily to interpret the volcanology, although we did all the field work together.
Was there a lot of work tracking down the photographs and interviewing locals? See if
Most of the
anybody's still-
photographs came from park archives. So we were able to go into the park and take a look at stuff. There was nobody there that curated them, nobody that really knew what they had. So it was a fair amount of work to go through them, pick out the ones that we thought were important. Among 1,000 photographs, there are 50 that are important. Make copies of them and then study what they actually were, because they were not curated. Some of them had dates, some of them had other minimal information, but a lot of it we had to figure out. Then there also, you can accumulate photographs from other archives. UC Davis has an archive. There's an archive at State Library in Sacramento. And occasionally you can find things on the internet. This is a copy, an original print of the critical May 19th photograph. As far as I know, there are only 2 of these in existence. One in the park archives, which has a bunch of annotations on the back, written by a guy named Dittmar, who was instrumental in getting the park created as a park. And this one, which I bought on the internet for $15. I searched for Lassen stuff on the internet all the time. I came across this picture, and I recognized that it was a very important picture, and I wanted an original copy for myself. So there are probably others out there that Loomis printed and gave away, but I don't know of any.
Where was this?
It was on eBay.
No, I mean.
There was a woman about 5 or 6 years ago, and I got this before that, but there was a woman about 5 or 6 years ago who, Loomis had no sons, so his family name did not continue. He had one daughter that died young, in her early 20s, and she did not have children either. So the Loomis side of the family died out with him. But his wife's side of the family continued on, and I think that this person was a grandniece or something like that, that was selling a lot of Loomis glass plate negatives on the internet. Very few of them were interesting. They were all kinds of photographs that I wasn't particularly interested in, although the park was interested in some of them. But so I really don't remember the details about where this came from. I had some information at one time, but I could probably go back and read it, see what I wrote at the time. I just don't remember it tonight.
Yes, we went on a family vacation to Lassen years ago, and what I remember is this boardwalk that we walked along. And over here were these fumaroles with bubbling hot water, whatever. And then there was a story of a school teacher that had her leg fell in, so the children were all, we were very, cautious about walking on this boardwalk. But I wanted you to comment on these fumaroles, because at the time I had no idea what they were. And so now it's interesting. What are they from?
Well, Lassen has the best geothermal system in the Cascade Range, the biggest and most developed, and it's actually the biggest in the United States outside of Yellowstone, which is, of course, world famous. The fumaroles are water that is basically meteoric water, percolates down into the earth from snowmelt and rainfall, and is heated by some body of hot rock that's underneath Lassen. So we know that there's still rock down there that's at least 500 degrees, and in fact, we think there's magma down there that's probably at a temperature of about 750 degrees. So this stuff, it percolates down there, gets hot, comes back up toward the surface, and boils from a reservoir that's about a mile down beneath where the fumarolic areas are. So the fumaroles are basically steam that's coming off of that boiling reservoir that's about a kilometer down.
Has the area where the fumaroles are, has that changed?
The areas where the fumaroles are change dramatically from year to year. Old fumaroles die, new ones start up. One of the people that I've been working with here at the survey, Patrick Muffler, is an expert in this area. He's done a lot of mapping of the fumarole systems and been able to document changes. One of the places that we were consulted on relatively recently was Sulphur Works, where fumaroles are coming up underneath the park road. And we were able to document their migration beginning in the early 1980s toward the park road. And last year, 2 years ago now, the Park Service did an extensive renovation of that part of the road. But they engineered it very nicely so that it's actually slightly elevated with an airway underneath it to allow the steam to vent and come out the side rather than eat the road.
I'll have to go again and see that.
It's so well done that you won't even notice unless somebody takes you and shows you what they did.
So we've had many of the serious questions. I have a somewhat more flippant question. There are some coincidences here that I think need to be addressed. One is that we have May 19th episode of eruption in 2 major volcanoes in North America in the last 50 years or so. Okay, so Goldfinger told James Bond that once was coincidence, twice was something or other. The third was enemy action. But the question I really have, and this is the more serious one, is both of these volcanoes seem to have blown in a direction to the northeast. Is there some structural characteristic of the way the plate tectonics occurs here that makes it more likely that these volcanoes will blow to the northeast? And is there a predictive value there?
That depends on what you mean by blowing to the northeast. The eruption columns are primarily ejected vertically, and they are blown by whatever wind patterns that you have on that given day, so that the wind, on average, is probably 50%. On 50% of days, the upper level winds are to the northeast in the Pacific Northwest. So that's the most common direction for deposits to go. However, for example, in Mount St. Helens on July 22nd, the winds were in the opposite direction and the ash went to Portland instead of Montana. However, I will also say that most volcanic edifices have some kind of structural control that is either internal to the volcano itself, the way it's actually been constructed, or is related to faults that underlie the volcano. So structure is very important in the individual growth and history of volcanoes, but there's no one rule that solves all of those questions. As for the coincidence of May 19th versus May 18th, I've thought a lot about that, and you're not the first person to ask that question. And it's interesting to note, Mount St. Helens probably had nothing to do with it being springtime, because it was a bulge that was created by intrusion of magma into the volcano. And as the bulge grew and grew, it destabilized the volcano, and it went when it was ready to go, when it got destabilized enough to avalanche. And there's still some controversy about whether the earthquake triggered the avalanche or the avalanche triggered the earthquake. We really don't have a firm answer for that. And I see Jim Moore sitting in the audience here, who was a person who was there at the time. So Jim might have something to say about that. As for Lassen, there was repeated activity in the spring of each year. And for many years, I've assumed that that had something to do with snowmelt percolating down into the volcano. But if you talk to hydrologists, they'll say that you can't get the water down there fast enough to make some kind of regular every spring that happens. In addition, my work on the magma mixing that created this eruption suggests that the mixing event happened about 18 months before the eruption itself, and that it's controlled by turbulence in the magmatic system and that churning over and ascent of the magma, and it just erupts when it wants to. It doesn't care about what time of the year it is. So nevertheless, there's a coincidence.
Two-part question. I'm interested in the future, and I'm wondering what you have learned about Lassen. Is that helpful in predicting when the next eruption of Lassen might occur, and also when and where
might the next major eruption in the Cascade chain occur?
Okay, I'll take the second question first because that's the simple one to answer. The Mount St. Helens is clearly the most active, the youngest, most active volcano in the Cascades. It's the one that's had the most activity over the last, let's say, 4,000 years, and it is the one that's most likely to erupt again. Nevertheless, that doesn't mean that it will be. It's just the one that's most likely on a statistical basis and a recent history basis. As for Lassen, we've learned a tremendous amount in the last 30 years, and we're continuing to get new information. For example, we didn't know for sure that there was magma underneath Lassen until very recently. A study that was recently done on zircon crystals, which are a kind of crystal that grows in the magma and has enough uranium and thorium in them that you can actually date these things, and we date them using the ion microprobe over at Stanford, has told us that there is an active magmatic system beneath Lassen. There's magma down there, but that it is mostly crystalline. So it's about 50% crystals floating in 50% liquid. That's probably too viscous to erupt on its own. The crystals, once the crystals basically start touching each other in the magmatic system, it behaves more like a solid than it does a liquid. It's much more difficult to deform. It's much more difficult to make it erupt. So what happens in a system like Lassen is you have this stuff, which is basalt that comes from much deeper in the crust. It intrudes that crystal network, and because that kind of magma is much hotter, it heats it, melts some of the crystals, stirs it up, and turns it back into an eruptible liquid. So that each of the eruptions at Lassen over the last 100,000 years has been the result of intrusion of basalt into the magmatic system, stirring it up and basically rejuvenating it. After the eruption, which removes most of that basalt and the stirred up magma, it goes back to its quiet repose of an interlocking crystal network and becomes uneruptible. So how often do those magma mixing events occur? Well, on average, it takes about 7,000 years, but in reality, they tend to occur in little clusters. One of the things that we're doing at Lassen now is we have a very nice seismic network set up there that we can see intrusion of basalt that's coming from much deeper in the Earth's crust and watch its migration coming up to the surface. So the next eruption will probably have some warning, and it could be weeks or months. It could even be longer than that if we're paying enough careful attention.
Thank you. Can you add two more parts? One is, what about Mount Rainier? And the second part is, what is the status of funding for volcanology in the current environment of the United States?
I don't want to say too much about the current environment of the United States. The Volcano
No, I asked about funding.
Yeah, the Volcano Science Center has a stable funding. It's enough to run what we have, to do the monitoring that we do, and some of the mapping and other volcanological studies that we do. If we had more money, we could do a lot more. We could learn more about the young volcanoes. We could study them more extensively, develop more of their history, and put a better monitoring system in place that would give us early warning. Now, unfortunately, the Cascades are not the biggest part of volcanoes in the United States. Most of them are in Alaska, and they mostly are on trans-Pacific airline routes, cargo routes. And it's very important to study those, to understand when those volcanoes are going to erupt, to get planes out of the way. I mean, you've probably all seen the stories about planes that fly into volcanic ash clouds and how it melts in their engines and basically kills the plane. So it's very important to keep those routes open, and that's where we're spending most of our money on monitoring Aleutian volcanoes, which most of the time you can't see because of the bad weather. So there's many pictures that we have of satellite pictures, for example, of eruption plumes coming up through clouds. People on the ground, there's no people in the Aleutian Islands, but there's very few people. People on the ground don't know the volcano's erupting, but we can see it from satellites. Now, I missed the first part.
Mount Rainier.
What about Mount Rainier?
I've heard that an eruption there may be coming in the reasonable future.
Well, there's no evidence that Mount Rainier is going to erupt anytime soon. It's an old volcano, as opposed to Mount St. Helens, for example. That's a young volcano. And it does not have eruptions very frequently anymore. The last was about 2,000 years ago. However, Mount Rainier is a huge pile of unstable, partially hydrothermally altered rock. The biggest dangers from Mount Rainier are collapse of part of the volcano. And this has happened in the past. There are two major collapse deposits that reached the area of Seattle in the last 5,000 years. So any kind of magmatic activity on Mount Rainier could provoke a major collapse that would be a serious problem for Seattle.
And the time
And it doesn't even have to be magmatic. It could collapse on its own.
And the time constant is 1,000 years or so.
Well, there aren't that many. There's two of these deposits. One's about 500 years old, and the other one's about 5,000 years old. But as I mentioned earlier, these things don't happen on regular time scales. They're episodic, and for an event like Mount Rainier collapsing, it probably needs some kind of trigger. However, for example, the big earthquakes that we have here in California, they also have in Washington on the subduction zone. There hasn't been a big one since the year 1700. There hasn't been a big shaker. And they have this 400 or 500 year recurrence interval for the really big earthquakes. So the last one was 300 years ago, but one could happen at any time. And that could have a serious effect on the city of Seattle and Portland, not just because of the earthquake, but because of the potential collapse of a mountain like Mount Rainier.
Thank you.
A second bite at the apple. Two items. One is the fumaroles. If I heard you correctly, was it meteoritic water? Very old water?
They are mostly meteoritic water. There's a very small component of magmatic water that's coming off the whatever magma body there is down there. And some of the gas that is in the fumaroles is also coming from the magmatic body. But the more than 90% of the water that's coming up is meteoric water, just rainwater that's percolated down to become groundwater.
Oh, not really old, ancient water. So the isotopic profile is not really old.
No, it's not old.
Not ancient, okay.
The isotopic profile is the same as rainwater.
Yeah, okay. I misunderstood.
Yeah.
The second one was in spring. You have the time of the moon, the sun are more aligned in a straight line, and you get your eclipses and so on. Mm-hmm. You get a bigger. You have those, of course, twice a year. Once the other time is in spring, but in fall. But in spring, the change, the delta change, would be bigger, because. And it might not be the direct cause, but it could be a factor in priming the pump, if you would, for a susceptible system.
Well, I don't know very much about that topic in particular, but I will say that there are people that work on this stuff, and they add earth tides to the stresses that are involved in volcanic edifices and magma chambers, and they are relatively small compared to the stresses that are created by having this body of hot magma in the earth. However, you're talking about a potential tipping point, i.e. a trigger for a system that's otherwise primed and ready to erupt. It's entirely possible that some kind of earth tide situation could trigger the event.
Thank you very much.
This has been a wonderful collection of good questions from everyone tonight.
One more, please.
Is it quick?
Yes.
Okay.
Mount Rainier, you said...
I'm here for the duration.
I'm from Seattle. And you mentioned Mount Rainier collapsing and reaching Seattle. What do you mean by reaching Seattle? Is this a mud flow?
Yeah, what has happened in the past is that the upper part of Mount Rainier is hydrothermally altered. And that means that the rock has a significant clay component in it. You get clay wet, it's very slippery. And it collapses, it gets water from the water that's contained in the rock, it gets water from valleys that it flows down, and it basically creates a mud flow. So the Electron and the Osceola, which are the two mud flows that have affected Seattle, mostly the Tacoma area, but into the outskirts of Seattle, those were mud flows that traveled down, I guess it's the Puyallup River.
Puyallup, yeah.
Yeah, and one of the other river valleys there. And because they're confined by river channels, they can flow a long way, just like they did at Lassen. The bigger the volume, the more the water, the farther it goes.
Thank you.
Well, I do want to thank Mike Klin for a wonderful talk about Lassen. I want to thank all of you for joining us tonight. Join us at the park on Memorial Day weekend. We'll have hikes and talks and all kinds of interesting things in the park. And join us again next month on May 21st for a lecture about earthquakes. Thank you and good night.